Welcome to Summarize Science. Have you ever wondered if the artificial intelligence on your phone and the brain in your head share more than just a passing resemblance? A groundbreaking new paper suggests they do, revealing that a unified framework from physics might underlie them both. The researchers show that equations used to describe neuronal avalanches, which are cascades of activity in living brains, can also be applied to AI. Think of a signal traveling through the layers of a deep neural network. If the network's connections are too weak, the signal fizzles out and information is lost. If they're too strong, the signal explodes into chaos, also destroying the information. The key, they show, is to be poised right at the edge of chaos, a state physicists call criticality. In this state, information can flow deeply and reliably through the network, which is essential for learning. However, both brains and AI are constantly being driven by strong inputs from the world around them. This means they don't operate at a perfect critical point, but in a quasi-critical regime, always hovering near that sweet spot. To prove this, the scientists looked for evidence of crackling noise, a set of statistical patterns that are a dead giveaway for systems near a critical point. They analyzed cascades of activity, or avalanches, in the AI and found these exact patterns, with their sizes and durations following specific mathematical laws. But here's where it gets really interesting for building better AI. The study found that proximity to the critical point isn't actually the best predictor of how well an AI will learn. Instead, a more reliable measure is the network's susceptibility, which is its sensitivity to tiny changes in its internal connections. The networks that learned best were the ones with the highest susceptibility, meaning they were most responsive. This region of maximum sensitivity forms a kind of map, called a Whittam-like line, which turns out to be the true roadmap for trainability. This explains a long-standing puzzle, why some networks that seemed to be at the edge of chaos still failed to learn well. They were on the edge, but not in the zone of highest sensitivity. The team even tested complex, state-of-the-art networks like ResNets and found they also obey these rules, though they belong to a different, universality class of criticality. So, let's recap the important points. First, both brains and AI appear to operate under the same physical principle of quasi-criticality, staying balanced at the edge of chaos to process information. Second, maximal sensitivity or susceptibility is a more important guide for performance than criticality alone, giving engineers a new target to aim for. What could this mean for the future? This work provides a physics-based playbook for designing and steering the next generation of AI. By understanding these fundamental laws, we can potentially build more powerful and efficient learning machines. It's a massive step towards a common physics for both deep learning and brains, bridging two of the most exciting fields in science. Thanks for tuning in to Summarize Science.